Software development meant writing code for a single, isolated machine. Today, applications operate as massive, multiplying webs of interconnected digital nodes, communicating globally. This diagram illustrates the baseline architecture for that networked world. Notice how even an individual developer or a small organization must now plug directly into a complex, distributed routing infrastructure to function. Java Standard Edition provides the core programming language and virtual machine for executing code on a single device. Java Enterprise Edition builds on top of SE, supplying the distributed APIs and runtime containers strictly required to develop large-scale network applications. While Java SE handles the internal mechanics of a single device, Java EE exists to manage the orchestration required when that logic is distributed across a global network. But scaling up introduces a severe architectural problem. The underlying hardware, network requests, and security protocols rapidly form an unmanageable tangle of complexity that overwhelms the developer. This model demonstrates Java EE's primary solution to that problem. The platform operates as a clean abstraction layer. It entirely isolates your core business functionality, the orange block, from the chaotic enterprise infrastructure underneath it. This architectural diagram shows how that central abstraction solves four specific operational challenges. By managing the underlying mechanics, Java EE allows an application to inherently run as a secure, reliable, multi-tiered, and large-scale system. This schematic traces how that abstraction is built. Through the Java community process, input from industry experts and open-source groups is fed through a convergence funnel to forge a single, unified Java EE standard. This portability matrix illustrates the immediate benefit of that strict standard. A single Java EE application can be deployed seamlessly across over 20 different compliant implementations, like Glassfish or Tomcat, without rewriting the code. By hiding the network mechanics behind a standard interface, engineers can focus their time exclusively on solving business problems rather than rewiring servers. This transit map serves as a visual primer for software communication. Moving data safely through an enterprise system requires distinctly different routing mechanisms depending on where the data originates and where it needs to go. APIs act as transfer stations, bridging the internal network to the outer world. REST is the high-speed intercity rail, dictating data travel across the internet. CDI is the intracity subway, operating exclusively within the core platform to route internal commands. Preventing a server from crashing requires strict adherence to these boundaries. You have to use the right communication protocol for the right architectural layer. This schematic defines an API. It acts as an explicit software intermediary, shown here as puzzle pieces, allowing two distinct applications to interact securely without exposing or understanding each other's internal code. This flowchart highlights everyday APIs in action. When a user checks the weather, sends an instant message, or interacts with a social feed, an API acts as the invisible messenger, delivering the request and returning the data. This diagram illustrates representational state transfer, or REST. It acts as the foundational language of the Internet, used by client browsers to reliably transfer data states across the web to the server hardware. This chart breaks down the exact mechanism of REST. It uses four specific lanes of web traffic, standardized HTTP commands like GET, PUT, POST, and DELETE, to route data requests to the server. This network graphic shows how RESTful APIs form the scalable communication backbone for the world's largest digital ecosystems, connecting platforms like Amazon, LinkedIn, and Google into a centralized hub. REST provides the universal language-agnostic agreement that allows completely different systems to exchange information across the web. This grid represents the internal environment of the Jakarta EE platform. Once external data crosses into the space, the internal software components need a highly organized system to communicate with each other instantaneously without relying on HTTP. This diagram maps contexts and dependency injection, or CDI. The CDI manager acts as an intelligent internal switchboard. When an event fires, it checks a master list and strictly determines which internal listeners to call. This table explicitly contrasts the two protocols. REST operates externally, transferring data states over the internet via HTTP. CDI operates purely internally, routing event triggers, and managing dependencies within the server platform itself. If incoming REST data triggered internal functions directly, it would cause chaotic, overlapping executions. CDI acts as an internal traffic cop to maintain order. This process diagram maps a complete data request lifecycle. A mobile app makes an API request, the browser uses REST to transit the data over the web, the request hits the backend server, and the internal framework fires a CDI event for execution. Looking closely at the bridge in this illustration, we see the payload itself. It travels as JSON, or JavaScript Object Notation, a lightweight syntax carrying the exact data across the REST API and directly into the server's business logic. This architectural model shows exactly where that business logic lives, Layer 3. This tier exclusively houses the managed components that encapsulate core functionality, such as Enterprise Java Beans. Below that is Layer 4, the Enterprise Information Systems tier. The actual underlying data resides completely separately here, often on different hardware, and is accessed exclusively by the business tier through low-level APIs like JDBC. Tracing a single JSON payload from a mobile interface down to a database row proves why enterprise applications rely on strict physical and logical layers to manage scale. This diagram illustrates a recurring enterprise challenge. Deploying a distributed system without unifying structural logic yields chaotic, failing connections. The solution is Java EE patterns. These standardized structural blueprints use a strict layered approach to guarantee specific quality of service. This diagram breaks down a widely used pattern, Model View Controller, or MVC. It rigidly enforces the separation of data and business logic in the model, the interface in the view, and request routing in the controller. These design patterns are not stylistic preferences. They are the load-bearing engineering rules that keep an application from collapsing under its own weight. To accelerate build times and reduced configuration overhead, modern engineering frequently utilizes agile frameworks on top of the Java EE baseline. This schematic shows the Spring framework. It acts as an agile structural scaffolding that surrounds native enterprise components. It is a highly popular open-source alternative focusing heavily on dependency injection. This comprehensive map outlines the modern Java EE landscape. The ecosystem has evolved to modernize support across the web, business, and data tiers, integrating enhanced data exchange and asynchronous event processing. Mastering these architectural abstractions, whether deploying native components or frameworks like Spring, is the definitive threshold between a standard coder and an enterprise software engineer.